Going to talk about Hess's law a little bit and how that works with thermochemical equations. Hess's law deals with steps of a reaction and how those work together to give you the overall enthalpy change. If we look at a reaction of C plus O2 yields CO2, and we have the delta H of that particular reaction is negative 393.5 kilojoules. We look at the second part of that reaction, which is carbon monoxide plus 1/2 O2 to yield CO2, and its delta H value is negative 283.0 kilojoules. What Hess's law says that if you don't have a calorimeter or a way to actually measure it, the best way is to look at the reaction as sum of the steps. Remember, it's a state function. The total enthalpy before and after the solution is all that's what matters. It's not the intermediate steps that get there. If we're trying to find out the overall reaction we're trying to get to is C plus 1/2 O2 yields CO, and we want to find out what that overall enthalpy of that reaction is, these two steps have to add up to this. We have to look at the stoichiometry and look at the coefficients that go in front and see how those relate to the energy values that are included. You have to look at what your base reaction is that you're trying to get to and try to manipulate these to get them to equal this when you put them together. With Hess's law says that whenever you flip a reaction, the magnitude of the enthalpy is the same, but the sign is opposite. And then anything that adds together will give us the total enthalpy by the time we're done. Again, it doesn't matter the steps that get there, it's the overall net change. So if you see this reaction to begin with, we've got the C plus the 1/2 O2. If you notice that CO is on a product side of this type, that tells me that CO is going to have to get to the other side, so I'm going to have to flip this reaction. So when I flip this reaction to be CO2, and on the other side is CO plus 1/2 O2. So I flipped it completely around. And what I want to be able to do with that is once I flipped it, I have to change the sign for the enthalpy. So it's the same number, but now it's 283.0 kilojoules because I flipped it and I reversed it around. Now, we want to see if everything's going to work out. I've got carbon, 1 mole on each side. I've got O2 here, but I have a 1/2 mole of O2. They're kind of like terms on both sides. This 1/2 O2 will cancel out on this side, leaving me with only 1/2 on this side. The CO2s are common factors over here, so they're going to cancel out completely from the reaction. So when I get done and I sum these together, I get the overall reaction that I was looking for, 1/2 O2 to make carbon monoxide. I can find the enthalpy of this by now putting these two together. I've got negative 393 and a positive 283, so we end up with a total enthalpy of this reaction of negative 110.5 kilojoules. The critical part to this is to realize that the stoichiometry of the coefficients in front, we can move these around and flip them around as long as we know that the enthalpy sign is the magnitude is the same, but the sign would be opposite. And that's usually in a 2-variable equation. It gets a little trickier whenever we deal with 3-variable equations. We have 3 different reactions that add up for enthalpy in Hess's law. Again, we're not measuring this directly. We're looking at the stages and the standard enthalpies that form. If we look at the overall reaction of 2 C's plus hydrogen to yield C2H2, and that's our overall reaction. And if it proceeds in 3 different steps. So if we have carbon plus O2 to yield CO2, and then we have H2 plus 1/2 O2 yields H2O. And then finally, if we ended up with H2O plus CO2 to yield C2H2 plus 5/2 O2. So there's 3 reactions that we've all put in there together to try to organize this. So as you look at the different parts and how this works, trying to look at how to get to the final reaction, we need to know the enthalpies of each of these. Notice I'd have to get 2 of the carbons. So if we looked at carbon by itself, in this one reaction, it's 393.5 kilojoules. That's its enthalpy of formation. When we look at the H2 plus 1/2 O2, that's negative 285.8 kilojoules. Again, these are the delta H values for these steps. And then this bottom one would be a positive 1,299.6 kilojoules. Now, as I look at this, I know that I have to have 2 moles of carbon in my final reaction on the reactant side. This has only 1 mole. So I need to double this. If I double it, I have to double everything in the reaction for 2 O2s, 2 CO2s. Since enthalpy is a state function, it's dependent upon the mole ratios, I have to double this as well. So the new enthalpy of this, whenever I double it, is negative 787.0 kilojoules. That's my new enthalpy because I had to double everything in that reaction. Now as we look at to see how things start adding up, when I've done that, I know that I've got to get rid of the CO2s. I have to take care of those by the time I get finished with this, with the CO2 values. When I look down here at the H2O, I'm trying to cancel things out. 2 O2s are on this side. I've got H2O here. I need to look to see what I can try to cancel out by the time I get finished. Looking at the reaction and the enthalpies and how it works, I got 5/2 O2, I've got a 1/2 here, and a 2.5 here. These are all going to cancel out, because this is on the reactant side, this is on the product side. Those are equivalent to each other, so they're gone. Now, CO2 values, and this is a 2 down here. That 2 CO2 in that original reaction is out of there now because I had to double that in the stoichiometry part. The water is the same on both sides, so it's out of there. So now we're starting to get it down to what we really need. We have 2 carbons, 2 moles of carbon, that's true. We have 1 mole of hydrogen as a reactant, that's true. Over here we've got C2H2. So we've got everything canceled out in the base reaction. So the only thing I have left is 2 carbons as a reactant, plus 1 mole of hydrogen. That's the only thing on the reactant side. Then on the product side, we've got 2 C2H2. So the big key to this one is realizing that I had to double this coefficient to make sure I get 2 moles of carbon in the ratios. So I've got a negative, I've got a negative, and I've got a positive. When I sum those enthalpies together, the overall enthalpy of the reaction is 226.8 kilojoules for the overall reaction. So instead of having to deal with a calorimeter or trying to measure it, we can look at the intermediate steps and the enthalpies, manipulate either the coefficients or manipulate the chemical equations to try to end up with our final balance. It gets tricky when there's fractions. In these intermediate steps, fractions are okay. Don't let that scare you. You just have to add them together to get them to cancel out and you start to manipulate them, all right? The other thing to remember is make sure you look for species that are like on both sides and try to get them to cancel with this net reaction. Again, it is a state function because it doesn't matter the intermediate steps. It only matters the final enthalpy of everything as is put together. Hopefully this will help you get the Hess's Law problems going in your textbook. If you got several odd problems, you can work out and see some examples as you do it. Thanks for watching, and then we'll do the enthalpies of formation next.